Okay, so this is a Physics 2022 paper. It's paper 1. Oh, I thought I was doing paper 2. That's why. Oh well, we can just do paper 1 as well. That's okay. 4 options are provided. 4 physical quantities are given. And always I'm going to ask, is it a vector or a scalar? So a vector has a direction and magnitude, and scalar just has a magnitude. So does the acceleration have a direction? Yes, it does. Does velocity have a direction? Yes, it does. Does displacement have a direction? Yes, it does. Well, distance doesn't. Displacement does. So I'm looking at option 3. Which of the following is the correct combination? Oh, the correct of a vector and a scalar. Oh, so speed has got to be number 3. And because that's a scalar, it only has magnitude, it only has a certain amount. So I would say 1 and 3 would be. Which of the following graphs best describes the relationship between the gravitational potential energy, so potential energy that's gravitational, and the height of an object? Okay, so my potential energy, what is my calculation for potential energy? Think about it for a while and let me know. Okay, so my EP is equal to, oh, and we just have height, so mgh. Mass, gravitational, which is 9.8, and the height. So how heavy that thing is, the gravitational potential it has on it, and the height above, because your potential energy increases the more height you have. If I've got 10 meters or if I've got 1,000 meters, this one's going to have more potential energy with the same mass. Okay, which of the following graphs best describes the relationship between the gravitational potential energy and the height of an object? Okay, can you see the gravitational potential energy, as the height increases, I have the same mass, I have a constant, and my potential energy goes higher. Can you see? This is very important to get this distinction. If I've got, I love VIR, I don't know why, I just love it. I can see that I is equal to V over R. The more R increases, the more resistance increases. If I've got a number like 1 over 5, and I suddenly make that number into 1 over 250. Can you see this one's tiny? So as resistance increases, then my current decreases. And that makes sense because resistance is resistant to the current. It doesn't want the current to go through. But if I'm at the top of the triangle, as the voltage increases, 1 over 5, which one is bigger, 1 over 5 or 20 over 5? Obviously 20 over 5 is bigger. And so everything goes back to this proportionality thing. And can you tell just from a formula which one is proportional? Now this is M times G times H is EP. So if my height increases, my potential energy, my gravitational potential energy, is going to increase. Okay? So that would be C. So it's just checking out your equation and seeing if height increases, and then put values in if you want. You can say 2 times 9.8 times 5. 2 times 9.8 times 10. Which one will be higher? Second one. So as it increases, this increases. Very important, this thing of directly proportional or indirectly proportional. 1 over P or whatever it could be. Okay, next one. A block of mass M slides across a frictionless incline. Not possible, but in real life, but we'll leave friction out. Plane RS is shown below. So friction is not there. Ignore the effects of air resistance. No air resistance, no friction. It's in a laboratory somewhere. So, it slides. Which one of the following mechanical energy of the block is correct? Okay. Mechanical energy of now. What is our law for mechanical energy? Mechanical energy is equal to my potential energy plus my kinetic energy, which is movement energy. Potential energy is talking about how high it can fall. What is the potential for it to fall from the bottom, from the top to the bottom? How far is that? That's why we got mgh in there. Height is very important. And also, your potential to fall has got to do with how heavy you are. Although if you drop two balls at the same time and one is heavier, actually, it's very interesting, they will hit the ground at the same time, depending, well, if, yeah, it will hit the floor at the same time. But if I take a paper and a ball, the paper will endure air resistance. That's another story altogether. Okay, so EP plus EK. EK is movement energy, so I'm going half movement, half mass times velocity squared. And all of this is just to say that my mechanical energy here at the top, my EP, say my EP is like, wouldn't be less than 5 because I got 9.8. So say for instance it's 50 joules. Which energy is measured in joules. You can check out the back of the chocolate packet. It's measured in joules. Kilojoules is thousands of joules. Okay, so say for instance it's 50 joules. As this goes down, my potential energy goes down and my movement energy goes up because it's starting to gain speed. As soon as there's no speed at all, there's no movement, and then it's all potential. But I'm looking at my speed on the way down, and what was my speed until I got there. So my mechanical energy at the end, my mechanical energy at the end is equal to my mechanical energy at the beginning. It's just that if this was 50 joules and I had no at the top and I had no kinetic energy, cool, 50 plus 0, then as I'm falling, maybe it goes EM is equal to, and I've got 25 joules. What will this be equal to? It'll be 25 joules of kinetic energy. Well, the equivalent. At the bottom, I've got no potential energy left because I've got no potential to fall. No gravitational potential to fall. So now I've got 0 joules. And what have I got here? I've got 50 joules, as you would like to say it. I've got 50 joules of this kinetic energy. And so by the time I'm falling right to the bottom, before I'm at rest and before the whole system stops, my mechanical energy doesn't change. It converts from potential to kinetic. Okay? And so at the top, it'll be exactly the same as at the bottom. So this one says this mechanical energy is bigger. No. This one says it's equal to. This one says the mechanical energy is equal to 0 at the top. No, it's got potential energy. This is a very important equation. That EM is equal to EP plus EK. Okay? So as this increases, this will decrease as it's falling. As it's falling. Until this starts 0. The movement energy is 0 at the top. But then the movement energy as it comes down, the movement energy starts to go up. But the mechanical energy stays the same at both points. So what I can really say in a very nice long way is that, what are we calling R and S? So I've got EM of R is equal to EM of S. And what I really can say is that EM is equal to EP plus EK. Plus EK is equal to EP plus EK. So what I really can say is, what is EP? Well, EP is mgh plus half mv squared. Please remember to square things. Square the velocity, please. Square the velocity. Okay, is equal to, and this is of, what is this called? R. And this is of R. And this is mgh, where mass is in kilograms. Gravitational is a constant of 9.8, it's acceleration, 9.8 meters per second squared. And h is just height in meters. So that's kilograms. That's meters per second squared. So G, M, and H. H will be in meters. If they give something to you in centimeters, please convert it. Cool, nice. Is equal to mgh of the S plus half mv squared of the S. And so, therefore, for 2 marks, which is 2 marks is important, we are going B. Okay, let's see. The identical metal spheres, Y. Now, please remember, grade 10, grade 11, grade 12, it's all one big thing. It's just, grade 11 is just an extension of this. 2 identical metal spheres, okay, so they're identical, suspended from long silk threads. As shown in the diagram, the sphere Y carries an unknown positive charge, okay, while sphere Z has a charge of -7 times 10 to the -9 coulomb. Coulomb of charge. Coulomb. I think it's got to be. Okay, so the spheres come into contact and then separate. Remember, when they come into contact, if I've got 4 here and I've got 4 here, well, that's not a good example. I've got 4 here and I've got 12 here. They come into contact and they take each other's average. So 4 plus 12 is 16 divided by 2, you're going to have 8. If I'm starting to get negative, so I'm going to say 4 plus -12 is -8. -8 over 2, which is 4. But we're going to say whether that's positive or negative. It's going to be 4 negative 4. Okay, so I got -7. The new charge on each sphere after separation is -5. So y, I don't want to make y x. X. We can make y x or y. Let's make it y. Why not? Why not? So y is y. So I've got an equation that I say y plus z times 10 to the -9 coulomb is going to be divided by 2 is going to be equal to -5 times 10 to the -10. Okay, so what I'm going to do is I'm going to times by 2 both sides to get rid of that 2, and just basic maths, I'm going to say y is equal to -5 times 10 to the -10 times 2, and then minus -7 times 10 to the -9. Okay, cool. And that should give me, let's just pause, and I want to do another calculator, make sure. And my calculator just gave me 6 times 10 to the power of -9 coulomb, which means it would be B. Okay, that's quite an easy one as well. Some of these, you've got to really think about them. 2 marks is a lot of marks. At the end of the day, 2 marks is a lot of marks. So you add them, divide by 2. if they give you one of the variables, find one of the other variables. Cool. Ooh, static, is a static electricity? Cool. After rubbing a polythene rod on the hair, a girl put the charged rod near a slow stream of water as shown below. Please do it yourself. You can do it with a glass rod. Glass will pick up with some of the static. Do it with a glass rod. You can probably even, I wonder if you can do it with just a normal glass. And rub it on your hair, rub it, or rub it on wool, or a cloth, and then put it against the stream of water, the tap. It's quite interesting. Science is doing, not just theorizing. Okay, what conclusion can be deducted from the observations pictured above? Okay, the rod acquired electrons rubbing against the hair. Yes, it did, because static electricity is, remember, electricity flows through, well, you still have lightning, but it flows through wires and it flows through conductors. Static electricity is static. You've got maybe some extra electrons on your hair or on wool, and they transfer onto the glass rod. And there's actually a table in your book for in the Doxentia book for what's more likely to take the electrons, what type of materials. So you'd want to take a glass rod or a glass. I haven't even tried it actually with just a drinking glass. I think I must do that tonight. It's going to take the electrons, and which makes it slightly negative. Okay, cool. So 1 is definitely yes. The net charge on the hair is negative. No, if I gave you electrons, I'm more positive. My hair is going to be more positive, so no. The water has a dipole charge. Dipole means there's positives and negatives, and we have seen that water is dipole. It's slightly positive and slightly negative because of the electronegativity of oxygen and its 2 hydrogen. So it's slightly negative on one side and slightly positive on the other side, which makes it dipole. And the positive side of the dipole bends the water towards the charge right. Why? Because positive attracts negative. Now this doesn't mean that girls must attract bad boys, but positive attracts negative, or in the same vein that boys should attract very dramatic crazy girls, but positive attracts negative. So 1 and 3. Where have we got 1 and 2? No. 1 and no. And 1 and 3. There we go. I like it. Consider the circuit diagram below. Okay, so I've got cells, and 2 or more cells is known as a battery. I've got an ammeter which tests my currents, and then I've got a split, so I've got in parallel. These 2 guys are in parallel. So my current splits here. So my A2 reading is going to be separate from my A3 reading, which is going to be separate from the whole. This is the whole of the currents, and resistance. Remember, resistors in parallel, R in parallel. 1 over R in parallel is equal to 1 over 2 plus 1 over 4, which is a half, plus, which is 3/4. But you're not done yet, because you need to take the reciprocal. So we're going to say R is going to be 4 over 3. I press the wrong button. 4 over 3 ohms. Okay, cool. So that's in parallel. And A2, now the current splits. So say for instance you have 8 here, you might have, depending on this, you might have 6 here and 2 here amperes. But let's see how this thing works out. Okay, How will the readings on the ammeters A1, A2, and A3 compare with each other? Okay, so can you see I just said the current splits? So if I've got 8 here, and I've got 6 here, and I've got 2 here, ampere, and I've got 6 ampere. Can you see the 2 plus 6 will give me that? Because it did a split. So some of it went there, some of it went there. Only when you're in parallel. In series, it's all the same. So I would say A1 is equal to A2 plus A3. Okay. Circuits get way more interesting. So you've got to get the small parts together and do a lot of exercises of just seeing how much current there is in each pathway. Okay, so I would encourage you to do lots and lots and lots of examples on just one thing before the exams. The exams become, I haven't seen this exam. I actually haven't gone through this exam at all. I just picked it out. I mean, this looked interesting. So these two circuits, okay, I don't see any. I've got a light bulb in. Okay, so this light bulb is in series to this resistor. A light bulb acts like a resistor, and this one's in parallel. But sometimes you get like lots of branches, and then you get a branch out here, and then you get a voltmeter doing something else here, and all sorts of things. You want to work on the one thing at a time. Just the current, just the current, just the current. Then I add more resistance. Then just that. Then I add more and I add more. So you want to start small, not on the big stuff. Okay. In the equation, okay, so velocity final is velocity initial plus the acceleration and the time it took to accelerate. Cool. The SI units for acceleration times time. Now let's think about acceleration times time. What is acceleration? It's meters per second minus 2. Okay. But if I say times time, what is time? Change in time. I'm going to say, now, can you see where this meters per second 2 came from? I usually do this, but they like to put it in exponential form. So, and it would be meters divided by seconds to the 2. Can you see how that's happening? This exponent, just in math, it came from the bottom. Now, if I times that by time, and time is measured in seconds. Well, that's delta time, which means change in time, but it's measured in seconds. If I times that by seconds, what have I got? I've got ms over s times s, because s squared is s times s. So, ms over meters second times second squared. Always go back to your formulas and go like, can I reorganize this? This becomes 1. I did this. ms, s times s. Okay. So I would be meters per second to the minus 1. So not meters. So even if you don't know what this formula means, it's fine. Just work it out. Go with the flow. Go with the flow. That's just acceleration. This is per second of something. I don't know what. And it would be d. Okay, so just go with the logical progression of taking apart the units, because they're asking for the units. Okay, consider the velocity versus time graph. Velocity versus time graph for the motion of an object. So velocity is meters per second, time is second. So the gradient velocity time graph represents change in y over change in x, which is gradient. And so that actually represents meters per second minus 1, or meters divided by seconds. Then I'm going to divide by another second. So per second, which would be times 1 over second, which is meters per second squared. What have you got? Bob's your uncle. Oh, meters per second minus 2. What have you got? Bob's your uncle. You've got acceleration. So the gradients on the velocity graph represents acceleration. Cool. Which combination below can be deduced about the acceleration in the above velocity time graph? Okay, acceleration. Am I am I having positive now acceleration is a vector, and because it's a vector I have direction, but they haven't given me direction, so maybe this is to the left or to the east or whatever. But can you see, if I'm in a car, I am putting foot. Constant velocity means over maybe 60 seconds or 3,600 seconds, which is 60 times 60. That's over an hour. I'm traveling at 30 kilometers per hour. I like to say hour like that. Per hour. Have I increased my speed? No. But as soon as I'm going 30, and then suddenly I'm going 40, and then I'm going 50, I'm going 60, I have put the pedal to the metal. I put the pedal to the metal. I put the pedal to the metal. What does that mean? It means I've accelerated. Okay, so negative and increasing. No, it's increasing. It's not negative. Negative will be going down. Positive and decreasing. No way. Positive and increasing. Okay, this is interesting. Now, although the velocity is increasing, my acceleration is the same. And you say, but why is that so? If I've got acceleration that looks like this, it looks like a curve, can you see that my acceleration, and this is velocity time, if I've got a curve, my acceleration is increasing. My gradient, can you see? My gradient here is maybe 1 over 1. Here it'll be like 2 over maybe 1.5. Here it'll be like 3 over 2. Can you see it's increasing? The gradient of the velocity graph is increasing. What's the gradient here? Here, y over x, 1. Y over x, I have no idea what 2 divided by 1.5 is. I don't want to pretend. Let me put it on the calculator. 2.5. Let's see. 2 divided by 1.5 is going to be 1.3 recurring. I should have known that. Sorry. Recurring. 3 over 2 will be 1.5. 1.5, and then it'll get steeper and steeper and steeper, and suddenly the gradient, we're talking about velocity, the y-axis, over the time, which is the x-axis. So the gradient is increasing. If I've got a straight line, what do I know about in maths? My y is equal to mx plus c. What do I know about my maths? If I've got a straight line, the gradient is the same. Gradient is constant. And I don't want to use the word constant too much, but the gradient is the same over here as it is over here, as it is over here, as it is over here. Same gradient. As soon as I have a curve, the gradient is different at every point. Meaning, here, the acceleration is not changing. The acceleration gradient is acceleration. Gradient of velocity time is acceleration. If the gradient is staying the same, the acceleration is not increasing. The acceleration is constant. The acceleration is constant. Here, in this curve, can you see my gradient is 1? My y over x is 1. Change in velocity over change in time. My y over x is 1.5. Maybe later on it'll be 1.9, 3.6. Can you see it's ever changing? That means my acceleration is changing. So be very careful that you don't see it going up like that and you say, oh, it's increasing. 2 marks is still 2 marks. 2 marks is still 2 marks. So, is my acceleration, and please use a highlighter to highlight words if you need to remember what you're looking at. There's a velocity time graph, but they're asking you about acceleration. But the more of this you do, the more you get used to it, so you don't get a fright in the exam and you don't misinterpret things in the exam. But be very careful. It's positive. The velocity is increasing, but the acceleration is not increasing. Acceleration changes only when I've got a curve in my velocity time graph. And so I've got a positive and constant acceleration. So maybe I'm accelerating at 1 meter per second. More in velocity. Okay, question 2. I wonder if I should break this up. It's been half an hour. Oh well. The head-to-tail or tail-to-head method of representing vector diagrams is one of the most scientific methods used to calculate the resultant force. So, if I go to the shop, this is home. If I go to the shop, here we go. I go to the shop, then I go to the barber. Okay, ladies don't really go to ladies don't really go to barbers. My distance will be, if this is 3 kilometers and this is 2 kilometers, my distance traveled will be 5 kilometers. But remember, if I want my displacement, I'm taking from there to there. And this will be my resultant, which will be my displacement. How much was I displaced from the beginning to the end? Displacement. Okay. Head to tail or tail to head. Can you see? My displacement or my resultant is head to head and tail to tail. Okay. Head to tail, tail to head. Method of representing vector diagrams is one of the most scientific methods used to calculate the resultant. Johnny moved from is a keyword, south to north for 4.5 kilometers. Okay. And then turn from north to west for 3 kilometers. Oh, I hope it's not one that we have to. Oh, it is. It's a scale diagram. That's okay. Just use your ruler. Make sure you got a ruler. Okay. 4.5 and 3. Okay, this is not going to be my triple. Pythagorean triple. Pythagorean triples are 5, 4, 3. That means this 5 is going to be a little bit extra, possibly. But let's see what the resultant is. Okay, so 4 and then 3. North to west, probably 90 degrees. Okay, define the term scalar quantity. A scalar has, and you're going to write there, magnitude only. Because for 2 marks, you don't want to just say magnitude. You're going to write a full sentence and you're going to say, a scalar is a physical quantity. Oh, let's say physical quantity. Because I don't think love or tiredness or anger is a physical quantity. Although maybe it can be measured in one's actions, possibly. Physical quantity that has magnitude, and please write the word magnitude. Please write the word only, so that there's no misunderstanding the fact that we only have magnitude and not direction. Okay, so use a scale of 1.5 centimeter to 1 kilometer. Okay, so you'll say 4.5 times 1.5 to tell you how many centimeters you've got. 4.5 times 1.5, 4.5 times 1.5 is 6.75. So this guy's going to be 6.75, and you're going to write it in. Make sure you write it in your 3 times 1.5 would be 4.5, I think. Yeah, 4.5. 4.5. And then you're going to make a nice resultant. Please make sure you put your heads or your arrows, that's the head, arrow, because I need to show the teacher where my or the marker or the examiner where my resultant is. And the resultant is always head to head, head to head, head to head. And I can see that that's where I ended. Okay, so I'm going to take Pythagoras. And these are draw the vector diagram to calculate the resultant displacement of Johnny. Cool. So you can say the net displacement if you want to. You can say net. I'd rather you just say hypotenuse squared. So we're working with a right angle triangle. Hypotenuse squared is equal to a squared plus b squared. Then net, because you can see this is a hypotenuse opposite the right angle. Net squared, or net displacement squared, however you want to say it, is going to be equal to, and you can put a square as the x value, and you can say x squared if we is x squared plus y squared. They should give you a mark for saying this, whether you said a squared plus b squared. I like this because it's mathematical, but this is the x-axis really, plus y squared is the y-axis. So what's on the x-axis? 4.5, 4,5 plus squared, please remember the squared, plus 6,75 squared. And you should get another mark for substituting in. But I'm going to square root this so that I can get net quickly. So I'm going to say the square root of this. So my net, where I'm going, or my resultant, you can also call it resultant, or resultant, would be, let's just see, 4.5 squared, 1.5, 4.5 squared is equal to plus 6,75 squared equals, and take the square root of that, 65,812, which is 8,812 squared to 8,11. 8,11. Oh, let me just pause and make sure. Yep, 8,11. Now you're not really actually done, because it's 8,11 centimeters. Now every centimeter, what's the scale? 1.5 centimeters is 1 kilometer. So if I've got 8,11 to something, if I want one used to calculate the resultant displacement, it's for 3 marks, so you should be able to say 8,11 centimeters, but we do want to find that out in terms of, oh wait, it says here verify your answer. Okay, so this was just the drawing. You get 3 marks for the drawing. 1, 2, 3. Verify your answer using the theorem of Pythagoras to get the resultant displacements. Fantastic. I like it. Resultant displacements of Johnny. Is there any similarity between the solutions? Of course there is. Yes. Bizarrely, yes. Yes, you can draw or use Pythagoras. Will work. So I've got 8,11, and I want to turn that back into kilometers. I don't think they find it necessary. I think centimeters fine, but he didn't actually go 8.11 centimeters. So I'd like to tell you how far Johnny really went. And so 1.5, I'm going to divide 8.11 by 1.5 and see where it gets me. So if I said from 3 kilometers to 4.5, I said 3 times 1.5. To get back to kilometers, I've got to divide by 1.5. So I said 8,11 divided by 1.5 equals 5,406 kilometers. Now I know that my Pythagorean triple is going to be 5, 4, 3. I know that. And if I've got a Pythagorean triple like this, and I've got 4,5 here, so this one's a little bit extra, and 3. That means that 5 is going to be, can you see that this 5 is going to be a little bit extra? So it does work out. Okay. So, let's see. Draw Pythag, same answer. Same answer. Okay. If Johnny decides to walk from north for 4.5 kilometers and then turn from north to south. Now, the real question is, did he decide from this point or differently? Let me just think and see if he decided from this point. Well, it doesn't matter if he decided from that point. We're doing a resultant of a new question, I'm thinking. Oh, okay, this is easy. Johnny decides to walk. Please make little diagrams on the side. Just like you do in trigonometry. I'm going to go all stations to Cape Town, and we're going to see who's positive and who's negative. Make little drawings. As soon as I read this, I made a little drawing. I went, oh, okay. He goes from south to north, and then draw this just in case we forget where east is. From south to north for 4.5 kilometers, then he turns from north to south for 3 kilometers. Easy. So total distance is 4.5 kilometers plus 3 kilometers. Remember, distance and displacement is different. Distance is a scalar, and this is what they're implying by asking you about your scalars, which is 7.5 kilometers. Then, this is a really easy question. My gosh. This is the Gauteng paper, 2022. Displacements. So, he's got 4.5 to the north. Choose north as positive. You can write that, choose north as positive. But minus 3 equals 1.5 kilometers. Now, where is he from where he started? He started here. I'm going to draw a resultant. Try and draw it in a different color. Works quite well. Where's my resultant is head to head, and my resultant is where I landed up. This is the start, and this is the end. So my resultant force, or my resultant displacement, is going to be, please, for 2 marks, you're going to give you 1 mark for 1.5 kilometers, another mark for saying north. And where's it north from? It's north from where you started. Please, you need to use this word from a lot. It's from and to. And it's 1.5 kilometer north. And you can say, if you want to, say from start. But it's implied it's from the start. Okay, cool. Question 3. This is not too difficult. Okay. At a construction site, a crane accidentally drops a block of mass, oh no, of 112 kilograms. Okay, let's start to make this list. Mass is 112 kilograms. Okay. From a vertical height of 10 meters. Oh, this is feeling like potential difference. Not potential difference. Potential energy. Potential difference. 10 meters. This is height. Height is 10 meters. And I know my gravitational potential is 9.8 meters per second. Ooh. Move this up. Meters per second, the 2. Okay. as shown in a diagram. So it has potential to fall. So it's here, and it's 112 kilograms. I don't know, it says that anyway. And it has the potential to fall 10 meters, but that's very heavy. Very heavy. It's like a rugby player, a very big rugby player, maybe Ibn Itzebeth. Ignore the effects of air resistance. Yeah, we always do. Until we don't, and then we're like, oh, what's going on? So it is here, and it's got the potential to fall 10 meters. So I'm looking at mechanical energy is equal to potential energy plus kinetic energy. Over here, before it falls, the kinetic energy is 0. By the time it gets to the ground, the potential energy is going to be 0, but this side is always equal to this side, so the mechanical energy is always the same. So I've got EM is equal to, that's mass, gravitational height, plus a half mv squared. Remember that square. Remember that square. Cool. State the law of conservation of mechanical energy in words. Like, we're going to draw it in a picture. I don't know. The total mechanical energy remains constant in an isolated system. What they mean by isolated system is you get this is just an example. You get 2 types of light bulbs. That's my light bulb. It looks like a balloon, but anyway. A sad cartoon. You get one with filaments, which burns nicely, and then you get an LED one. Now, the one with the filaments lets out a lot of energy in the form of heat energy. And so if you get a normal one from like 10 years ago with this not LED, you're going to have a lot of heat energy. So whatever the energy is that goes into the light bulb gives out light energy and heat energy. But an LED light bulb gives out lots of light energy and very negligible amounts, only a tiny bit of heat energy. Which one do you think will cost the most to run? This one. Because to produce the same light as this LED, I've lost of heat energy, which means I've paid more in electricity. And that's what they mean by isolated system. An isolated system, it doesn't mean you're losing heat energy or you're losing energy by air resistance or by different factors. That was just an interesting example. But in an isolated system, all the energy goes into light energy, and the rest is negligible. Okay. In a non-isolated system, all sorts of other things are working on that system to take energy out in different ways, like wind. Maybe the wind blows and it blows it around, and so and different things are happening. Okay, so say the law of conservation in words. You can say the sum of the gravitational potential energy and kinetic energy at the top equals the sum of the gravitational potential energy at the bottom. It's the same thing. EP at the top plus EK at the top equals EP at the bottom. But the sum of, so EP at the top is not going to be the same as the bottom. So you've got to say the sum of that. The sum of this is equal to the sum of this. Okay. But a nice way to learn it would be I'll write it out quickly. Okay, the total mechanical energy remains constant in an isolated system. That's the conservation law of conservation of mechanical energy. So I don't lose any, it just converts. It converts from potential to movement energy, kinetic. Okay. Determine the gravitational potential energy, okay, of the block at height 10 meters. Easy. 3 marks. You're going to write your formula. You're going to sub in, and you're going to get an answer. Very easy. EP is equal to mgh, 1 mol equals 112, because it's measured in kilograms. Make sure you get the measurements. It's got to be the right units. Times 9.8. That's a constant for gravitational acceleration towards the Earth, times 10 meters, which will give you 10,976. Please put joules there. Anything to do with energy, we're looking at joules. Okay. We've got watts and joules in electricity, but it's joules. Okay. So 3 marks, easy marks. Formula, substitutes, answer. If you leave the joules out, they either take the mark off or they take off half a mark. So remember joules, like on the back of a chocolate, kilojoules. That's 1,000 joules. Calculate the velocity of the block when it has fallen 2 meters. Now I've got 2 equations. I've got one for kinetic energy. Now it's fallen. When it's fallen 2 meters. Now it's not just sitting there and we're in a different system. It's fallen 2 meters, and as it touches the ground, I suppose, or 2 meters. So I've only gone 2 meters. 2 meters. So I've got kinetic, because it's moving, is equal to half mv squared. Cool. Velocity squared. So kinetic energy is going to be equal to half, and the mass is 112 times velocity squared. But I don't know my EK first. I need to find my EK. Okay, so let me just make some space. Okay, so my mechanical energy is going to be 10,976 joules, which is like almost 11 kilojoules. And my mechanical energy at the top is going to be the same as at the bottom. So what are you going to do? You're going to write out, color. So we're going to write out EP plus EK is equal to EP plus EK. So EP at the top plus EK at the top is equal to EP at the bottom plus kinetic energy at the bottom, because of the law of conservation of mechanical energy. Okay, so what have I got? I've got mgh here plus half mv squared. Please remember the squared. Mass, gravitational acceleration, height. Mass, velocity squared is equal to mass, gravitational acceleration, height, plus half mass in kilograms times velocity squared. So I'm looking to find my velocity squared, but be very careful. I'm not actually going to be at the bottom. The bottom is going to be 2 meters. The bottom is going to be 2 meters away. Wait, let me think. Height is going to be 2 meters. Yes, it's going to be 8 meters. Now, my new height, let's just do it in red. My new height is going to be 8 meters. Does that make sense? If I fall in 2 meters, what's my potential to fall? My potential to fall is no longer 10 meters. My potential to fall is 8 meters. Just be very careful of that. That you've got to minus them, because my potential to fall is not 2 meters, it's 8 meters, because I've taken away that 2 meters. So you've got to do quite a few of these to remember how that potential works from here to here. Okay, and then we just say, at the top, I've got already what I sorted out. I said MGH in this previous one. I said MGH is going to be 10. You can do it again if you want to. 12 times 9.8 times 10, which is 10,976 joules. Well, we don't have to say joules in between. Plus, now, even if I say half 10, can you see my velocity is 0? And anything times 0 is going to give me 0. So you can either put that whole thing in, or you can just put in 0. Doesn't matter. let's put it as 0 for now, so that we know that it's, as soon as you got velocity 0, the kinetic energy, there's no kinetic energy at the top. Okay, then at the bottom, well, we're not right at the bottom. Then I've got M. M is still 112 times 9.8, but it's going to change from potential to kinetic over here. Why? Because now this side is equal to this side, but now I've got 8 meters to fall potential gravitational energy, plus half, my mass is still the same, times 112, and then you just algebra it out, v squared. So what have I got? 10, 9, 7, 6. Put this in on the calculator so you can see it done separately. Let's see, 112 times 9.8 times 8, potential to fall 8, is going to be 8780, comma 8. That makes sense because I got a 0.8, not times 10. And then take it over to the other side, in other words minus it, both sides. 976, it should be 2195,2 joules, velocity squared. Ooh, not velocity squared, would be half of 112 is 56 v squared. So I'm just doing a bit of math. So 56 divided by 2, divide both sides by 56, divide both sides by 56, so divided by 56, and remember that that is velocity squared. So velocity squared is equal to 40. I've got hang on. At the bottom, yes. Sorry, I had a little thing here. It's 39, comma 2, which is 6. I've got to square root both sides, and velocity is going to be 6, comma 3. But if you want to be precise, let's put divide by square root of 39, comma 2. It's going to be 6,26. 6,26. Please put your units in. It's not 6,26 jelly tots. Meters per second minus 1. Okay, very easy. You need to put this is the same as this. The height changes here. This is 0, but we haven't gone all the way down. In a lot of examples, they go all the way down, and then this becomes 0. I just made sure that it wasn't 0. But we haven't gone all the way down. We've only got 8 meters left, and you kind of need to show that your height is now 8 meters from rest, from this, the lowest point, from the falling point. Okay, that was an interesting one. I like that because it wasn't falling down to the bottom. Okay, so velocity is 6.2, and that's for 4 marks. That's quite nice. Velocity is equal to 6,26 meters per second. Okay, fallen. Let me just clean this up a bit. Okay, prove with calculations that the velocity of the block is 14 meters per second upon striking the ground. Yes, I knew we were going in that direction because we always go in that direction. All the examples will be pretty much like this. Okay, so let's see. We're going to use mechanical energy, and you're going to say, you're going to say mechanical energy. You can say mechanical if you want to. Mechanical energy at the top, is equal to mechanical energy at the bottom. Now this is the real bottom, and so all I needed to do, I could have actually just left that there, but anyway, all I needed to do, the top was still 10, what is it, 10,976 plus 0 is equal to, at the bottom, can you see, well, what I mean by the bottom means upon striking, like just in this millisecond before it stops completely, because otherwise this will be 0. So that's what they really mean. MGH will be, and that'll be times 0. Do you agree? 112 times 9.8 times 0. When the height is 0, guess what? We've got no potential energy left. So you can write that all out, or you can just say 0. But just make sure that you're doing it in the right place and you are interpreting properly. So I got to do lots of these. Plus a half times 112 times velocity squared. Now this is going to be different because before we had a number here, because we had 8 meters to go. Now we have 0. So I'm going 56 v squared, 10976. Okay, so 10976 divided by 56. Oh, I should have put the square root there. The square root of 196 is v squared. So therefore, v is equal to, and I should know this one, 14. So v is equal to 14. Please put the units or you don't get the mark. Meters per second. Okay. So where are we going to get our marks? You're going to get a mark either for saying this first one or this one. This means the same thing. Maybe say the first one because we're implying the second one. Then you're going to get a mark for substituting. So we substituted here. Then if you put 0, you'll still get the same mark here. Then you get a mark here. 4 marks. How will the mechanical energy change? Is there air resistance? Is there something more in the system? Or is it still an isolated system? As the block is falling, right, only increase or decrease, it remains the same. Well, duh, it remains the same. We just said that 100 times. Yeah. It remains the same. Why does it remain the same? Because that's the law of conservation. Total mechanical energy is... in a system like that, when they say there's no friction, no air resistance, no friction, no wind, which is kind of air resistance, then you're in a closed circuit or an isolated system, and therefore it's conserved. So you can say no air resistance or no friction, and the total mechanical energy is conserved. Total mechanical energy. So you didn't lose some mechanical energy to the wind blowing it around or some kind of friction because it hit something on the way. Oh, don't hit something on the way. Don't hit someone on the way. Total mechanical energy is conserved. There was no air resistance or friction. Okay, this was a super easy question. I feel this is quite an easy paper. Maybe it's going to get more difficult later. Doesn't look like it. Oh well. Physics is easy. You just apply what you know. Okay, but you got to apply it a lot to get good at applying. Okay. Two identical metal spheres are suspended on light inelastic cotton threads. Sphere T carries a charge of plus 5.4 nanocoulombs. So I'm looking at 10 to the negative 9. Remember, we need to know what my nano means. Nano, pico, or my minus 6, minus 9, minus 12 stuff. Then, cool, so both 10 to, so times 10 to the negative 9 times 10 to the negative 9. Cool. Two identical sphere T carries a charge of that, sphere S carries a charge of that. Okay, so this one's got more electrons. They're going to come together, we're going to add them, divide by 2, and then they're going to be repulsed by each other. Why are they repulsed? Because now they have the same charge. Like charges don't attract each other, like charges repel each other. Like charges repel each other. Okay, so they're attracting right now, but later on, when they share their electrons, they are going to be repulsed by each other. They don't want to be in the same room. Okay, so, and it is an interesting question about magnetism. How can the north and the south, but that's poles. State the principle of quantization of charge. Okay. Quantization of charge means I'm not splitting electrons. That's pretty much. And you can extrapolate not splitting electrons. Don't say that in your exam. Not splitting electrons. If you remember not splitting electrons, you can extrapolate the definition from that. So every charge, these two are charges, like the glass rod and the hair and the water. Every charge, okay, every charge in the universe, even on Mars, consists of an integer. What does an integer mean? It's a whole number. So I'm not splitting that electron. Multiple. What are multiples? What are the multiples of 3? They are 3, 6, 9, 12. So here I have one of them, here I have 2 of them, 3 of them, 4 of them, groups of 3. Okay. Integers. Consists of integer multiples, or of integer multiples, or a multiple of electron charge. So if I go to my if you go to your the data sheet, can you see that my electron, the charge on an electron is going to be negative 1.6. Remember, a proton is also 1.6, but it's positive 1.6. It's negative 1.6 times 10 to the negative 19. It's useful to kind of know this off by heart so that we don't have to go back and forward to the data sheet, but it's on the data sheet. And look, motion, graphs of motion, all of these are on the data sheets as well, and we did this one already. And here we go. Electrical mechanical energy is EK plus EP. Some countries talk about it as U, and I suppose later on in physics in university we talk about U, but we're going to talk about EP, I suppose. And then we've got some wave stuff. Charge. Ooh, yes, please look at your chart. Look at your data sheet, because we're probably going to use this in 2 seconds, and we're probably going to use this in about 4 seconds. Okay. And then these are your triangles. I prefer them in triangles. So I, T, Q, and remember this is delta T, which changed in time. V, I, R. I don't know why they didn't put it here. Maybe you're just supposed to know it. It's one of my favorites. And then I always put what's at the top. I'm going to put at the top of the triangle. And then this is in parallel. This is circuits in parallel. This is the resistance in ohms, and this is resistance in series, resistance in ohms. Make sure that you know your units for everything and what everything represents, and then this one stuff will be amazing. So 1.6, negative 1.6 times 10 to the negative 9. Okay, let's see. I think it's just over an hour now, so I think I'll make we'll just do question 4, And then we'll do some of the electricity. Electricity look quite easy. This looks quite easy as well. Okay. State the principle of quantization of charge. Every charge in the universe consists of an integral multiple of electron charge. I don't want half electrons, please. So, calculate the number of electrons added to sphere S. Now, I just found my number of electrons in that data sheet. So, N is equal to my Q in Coulomb divided by, guess what? The charge of an electron. And the charge of an electron is a constant, which is negative. But we don't need to use negatives here because it'll just, it's electrons. 1,6, don't put the negative there. 1.6 times 10 to the negative 19. And what's my charge? Calculate the number of electrons added to sphere S. Okay. So it hasn't said that they have come together yet. So you've got to kind of, I like the word extrapolate tonight. They haven't come together yet. So if something has a negative charge, there are extra electrons on it. Maybe it picked up electrons from someone's hair. Maybe something rubbed against it and gave it its electrons. So how many extra electrons are put onto that thing so that it does have a charge? Even ions. If I talk about oxygen ion, so if I talk about an oxygen ion, it means it's doesn't have the same amount of protons as electrons. It means we've got a charge, positive or negatively charged. Okay, that's what an ion is. So I've got 8,2 nanocoulombs, which is times 10 to the negative 9. So N is equal to, you're going to get a mark for this. This is out of 3, mark for the formula. And the formula was in the formula sheet. So is the charge divided by charge on an electron. So, and that goes to show what they were pointing towards. So I've got 8.2. You don't have to put the negative. Well, you can put the negative, but we know it's electrons. Times 10 to the negative 19. Negative 9, sorry. Nanocoulomb, negative 9. And that is equal to 5,125 times 10 to the 10. If your calculator says e to the 10, please just make it into, I just want you to write here. Just make it into, come on. I don't like notifications. I feel like we need to turn off all our notifications on our devices because they distract us too much. Like as you're focusing on something, a notification comes up. I think we need to take them off. It's causing ADD in our growth factor of our concentration. So, and then you're going to say, what is this? It's electrons. The number of electrons is the charge divided by the charge on one electron. Doesn't that make sense? So I've got 5,125 times 10 to the 10 electrons. Okay. Now, attraction force. Let's see, what type of force is exerted by sphere S on sphere T? Right now they are attracting because they are negative and positive. So attraction. After they come together, they will repel each other. And this is it got some electrons through static electricity. Static electricity. The spheres are brought close to each other and then separated. Okay, so now they have bonded, and this guy has shared his electrons with T. Okay. Which field will electrons move? Well, obviously from S to T. That's pretty obvious. This is very easy. State the law of conservation of charge. Okay, there's a lot of laws of conservation in physics. The net charge. So the net charge, let's say of an isolated system of an isolated system. Remember, if there are other things acting on it, then we're going to lose some charge. So if my hair is rubbing against that thing while it's trying to give its electrons over, there's going to be weird things that happen. So net charge of an isolated system, no other forces acting upon it or other things, remains constant. During any physical process, during any physical, because it's not an abstract noun, process. Okay, the net charge means the overall charge. Overall charge, even when they come together and then when they separate again, it's still the charge of the whole thing is still the same. It just was, electrons weren't lost. This is really what this means. Electrons aren't lost. Electrons aren't. Who's the dude with a glove? With infinity stones. There's no infinity stones. Electrons don't disappear. They move, but they don't disappear. Electrons don't disappear. Which tells us about the charge. The charge net, the beginning is charge net at the end if there's nothing else going on. Okay, cool. So, electrons don't disappear. Use the law of conservation of charge to calculate the new charge on each sphere after separation. That's pretty easy. Q new. Needs to be a song. QQ me and you'll see. I think QQ me, like you would message. Q used to be the word for message, maybe. QQ me and you'll see my name on your PC. That's a computer. I know that you like me because you're still online. But now with WhatsApp, you can be online with 500 people. So it doesn't make a difference. But if you're online with that one person, it would have made a difference. So QQ. Charge of nu is charge of S of T plus charge of S divided by 2. They add together. So you get a mark for this out of 3 marks. Hey. Yeah, 3 marks. All of these are 3 marks. That's fabulous. Wonderful. It's wonderful. 5.4 times 10 to the minus 9. Remember that nanocoulomb. It means small charge. Divided by 0,000000009 of them. Okay. Plus negative 8,2 times 10 to the minus 9. 19. Now you can use the negative here because if I've got 2 positives here, I'm going to have a positive charge. If I've got a negative and a positive, I'm going to have a negative charge if the positive is smaller than the negative. And then divide that thing by 2 and you get a mark for that. And that'll give you 1,4 times 10 to the minus 9 coulomb. Cool. And another mark there. This is really a bit simplistic. Please learn your definitions. The definitions is where you could be losing some marks if you don't learn them properly. But you'll learn them perfectly and then you'll get all the marks. Okay, so 4.5. Use your knowledge of electrostatics. So electricity has got to do with statics. Static means it's staying in the same place. It means it's not moving unless there's friction or touching. Okay, so it's not just moving in the air. There's touching. Electrostatics to explain the phenomenon below. When the air is dry, your hands feel a small sharp electric shock. Okay. Ooh, that's got to do with humidity. when you touch a metal doorknob. Touch. You got to touch it. You can't just look at it and then you'll get a spark on your hand. Okay. Sharp electric shock when you touch a metal doorknob. Shame. Get some Vaseline. In South Africa. After walking along the carpet to the door. Oh, yay. So I go to the carpets. The carpets is going to give me some electrons onto my onto my shoes or onto my feet. Why did they say after walking along the carpets to the door? Let's break this down. I get electrons from the carpet onto my feet, maybe. But then the electrons would be on my feet. So that's a bit weird. Okay, let's leave that carpet walking first. When the air is dry, your hands feel a small, sharp electric shock. Okay, so humidity. When air is dry, there's less water vapor. Which means the humidity is low. When the air is dry, when the air is dry, I don't know. In my mind, you've just said the air is dry, but if it's very humid, it's talking about how much water vapor it can hold. So I'm thinking that the thing is that water molecules can collect on materials. When the air is dry, your hands feel a small, sharp electric shock when you touch a metal doorknob after walking along the carpet. I don't really like this one very much, because are you walking along the carpets with your hands? Like, okay, maybe you're walking along the carpet with your hands to the door. Then you get up off of your hands and you've got some extra electrons. You've got some extra electrons on the hands that you were just walking on. Okay, you're walking on your hands, and you got some extra electrons from the carpet. And then you touch a metal conductor of electricity, and you get a shock. Okay, that's the best way that I can describe this. And the air is dry. The air is dry. Remember, water is not a great conductor of electricity unless it's got like Na, magnesium, things like that. That's why when we put 2 electrodes in and we take sugar water there, and we put it to a battery, it's not going to light up. But as soon as I put salt in or magnesium in or some kind of metal in to that water, it's going to conduct electricity inside that water. But now if the air is dry, maybe there's less water, and so humidity does affect static electricity, because the electrons can go to your hands if they're not wet. I would just, this is a weird one. I would just say that your hands, after you've walked on your hands, the electrons rub off on your hands, and then you touch the metal doorknob. And because the air is dry, maybe your hands feel a little bit dry, and so the water doesn't restrict the flow of electrons. This is funny. If you've got a different interpretation of this, please tell me. It's an hour and 24 minutes, so I think I'll do question 5 and question 6 in another one just to save a bit of time, unless you want to do this one now, but let's just save a bit of time. Okay, so we're walking on our hands. Okay, well done.